Okay, over to you, Bob.
Thank you very much. It's a pleasure to be part of the SoundSoftware Workshop 2014. Thank you for the invitation to come speak. So today I'm going to talk about how reproducibility to scale towards article acceptance. And this is work done in collaboration with my colleague Fabien Guyon. And I'm at Aalborg University, Copenhagen, and he is at Enesh in Porto. So I visited Fabien about a year ago, and we came across this paper. I said, this is a very interesting idea. Have you heard of it? He says, yeah, we tried to implement this a couple of years ago, but we were unsuccessful at it. And I said, well, let's have a go at it. Let's try to reproduce the results, because I was very interested at the time in genre recognition. So the idea behind this intergenre similarity is very simple. It's very convincing. As the overlap between classes increases, it becomes harder to distinguish between the classes. So if we have two classes here in some feature space, and we have lots of observations of either one of them, it's quite rare that we're going to have anything, all the sub-observations or observations be in this shared portion. But as we increase the overlap, it becomes harder and harder to distinguish between the classes. We have to make more and more observations of a particular instance to make a distinction. So we focus on the differences to make a discrimination. So the IGS principle is to give more weight to attributes that are unique to each class in order to make the discrimination. So in music genre classification, it's described as follows. We have two classes, jazz and disco. These two classes of music share drums, for instance. So don't pay attention to the drums when you're making the distinction between jazz and disco. As we go to classes that overlap more, Baroque and classical, counterpoint is shared between the two. And then techno and trance, a lot of those type of music appear on vinyl records. So don't just look at the medium to distinguish between the two, but look at something else. Now that's a gross simplification of the genre recognition problem, but I'm trying to convince you the IGS principle may have something convincing about it. So building the classifier proceeds as follows. We take a training data set of labeled sub-observations. Now sub-observations in this case is individual frames of features that come from a longer audio signal. We model the sub-observations of each class using assumptions of independence, a naive Bayes model, mixtures, Gaussians, what have you. We classify each of the sub-observations in our training data set, and we relabel all the ones that are misplaced classified as being this intergenre class. So this is like modeling the intersection of the two circles in the Venn diagram. Then we relabel all of those as this intergenre, and then we model all the sub-observations again, including modeling this intergenre class. So now we hope to have models of the unique characteristics of each class, plus a model of the similarities between all the classes together. Kind of like maybe universal background modeling or something where you're looking to remove all the information that isn't specific to the classes. And then we classify an observation only from the sub-observations that are not classified as non-IGS. And so it's just maximizing the posterior, and we set each one of these weights to be 0 if the posterior probability of, or the posterior density of that in the IGS class is higher than any other class. So a simple example, two Gaussians overlapping. We take lots of sub-observations. It's going to be from either omega 1 or omega 2. This is distributions of the two. And it's quite rare that we're going to have all the sub-observations over in this area classified as omega 2 when it's actually omega 1. And so the center density here is the IGS density that we get from theoretical analysis if we know the true densities of the two. So any observation that lands between, any sub-observations between these two threshold, these two values, is thrown away. We don't pay attention to it because it has a higher posterior in the IGS class. And then so we pay attention to all the sub-observations out here for omega 1 and out here for omega 2. So to the greatest extent possible, we replicate the system that the original authors created and reproduce the experiments in the Zanatakas data set. In their paper, they have, as they increase the order of the Gaussian mixture models that are modeling each class as well as the IGS, they have an increasing classification accuracy from 66% to 76%. When we redid it, it went all the way down to 15%. And it didn't really increase as we increased the order of the Gaussian mixture model. So we thought, this is really strange. We played around, we fiddled with the weights, we debugged. We chose a different kind of weighting that paid attention to some of the IGS misclassified sub-observations, and we were able to bump it up quite significantly, but we were still far away from what was originally published. They had an experiment where they don't use the IGS weighting, but they use the models that were created for each of the unique portions of the sub-observations. And so not as good as results as the original ones that they had, but still better than far better than our 15%. And then when we perform the same sort of weighting, again, we have not quite different from this without the weighting, but still a little bit below what they had in their study. And when we just run naive Bayesian classification on it, we're able to bump it up quite a few points on most of them. So this was strange. We did a lot of debugging. We did had conversations with the authors that were very helpful. We were convinced in the correctness of our results, so we decided to sit down and actually analyze the problem. And so we sought to explain this discrepancy using a simple model first. We have two classes, Gaussian model. What happens? What's the probability of error for this IGS case and just naive Bayesian classification? So we discovered that the IGS is always suboptimal to a naive Bayesian classification. And that's expected since all sub-observations, even if they're in the tail of one of them, brings with it information. We see that the difference in probability of error between IGS and the naive Bayesian classification is greater than 0. It diminishes as we increase the number of sub-observations that we have. And it diminishes as we increase the distance between the two means, the two distributions. So we see here the solid lines are theoretical predictions of the difference in probability there, and the dashed line is a computational experiment, an average over several experiments of different sub-observations. So in some of them, too, it's interesting, the error between the two increases until a certain point and then starts to decrease. But as the number of sub-observations increases, the error diminishes to 0. Still a non-zero probability difference in probability of error. We decided to do a simple case that satisfies all the assumptions of IGS. Here we have 4 classes, and they're distributed such that one of the Gaussian distributions in the class is well separated from the others, and all 4 classes share a central characteristic. So IGS is going to see this portion and model these sub-observations as the IGS, and only pay attention to these. And we're going to draw two observations from each class and classify it. So in this case, we have a large separation between the classes and the shared portion. Naive Bayes error is about 0.197. This is a empirical, not a theoretical error. And the IGS is still inferior probability of error there. As we decrease the separation between the shared and the unique, we increase the error necessarily, but the naive Bayes still beats the IGS quite significantly in that case. And we make it such that it's very rare to have an observation, sub-observation selected from the unique portion, but still we see that the naive Bayes is worse than the IGS method. So we wrote up our results and submitted it to the IEEE letters, signal processing letters, and included MATLAB code that reproduced all our figures and tables. And after a few months, we got a rejection, but encouragement. Here are some of the quotes from the reviewers. At the current time, it's common to encounter papers describing computational results that cannot be duplicated. In fact, my experience is that it's extremely rare to encounter a paper that can be duplicated with any precision. Another reviewer actually worked with our code. I experimented with the code to see if I could find what was causing the very poor performance. It's, of course, a fantastic plus to the style of research that I was able to do this all. So, publishing well-structured code to regenerate every figure and table in the paper. The associate editor encouraged us to revise and resubmit and had several helpful suggestions. So we revised and resubmitted. We got 4 reviews back. The first reviewer recommended AQ with minor revision. This paper should be useful for the general signal processing community as an example of revisiting and reproducing prior research. Commendable is the fact that the paper is completely reproducible. The second reviewer recommended an accept. Since some reviewers expressed surprise at the difference between the results in this paper and the original, there might be some issue with the new implementation. I think the reproducible implementation is the one that should be taken seriously. Reviewer 3 said the journal should defend research and not debunk it, and so that's a reject. Reviewer 4 said reject, but he said a big pro of the paper is that the authors foster reproducibility. And it's really good practice of good science, but not unfortunately seen in signal processing and music IR domains. So the associate editor accepted the paper, having taken into account the quality of the reproducible research. So I really think this is a time where the analysis combined with the reviewers being able to reproduce all the figures in the paper and convince themselves of the correctness of the implementation and the analysis made the difference in the acceptance of the paper. And it now appears in a recent edition of the Signal Processing Letter. So there's 2 interesting lessons to this episode. When possible, analyze before implementing. A little bit of analysis shows how this very convincing idea turns out to be suboptimal. And when possible, reproducibilize before submission. So that reproducibility quality of submission and peer review can aid and sway acceptance of the article. So I wish to thank the associate editor, Kostas Katropoulos, and the reviewers for their helpful work. And this trip to Queen Mary is sponsored by the Reproducibility Prize that we won for this work last year. And the work on the IGS is supported by a postdoc grant I had ended this year in the COSOund project. So thank you very much for listening. Question session.
There is a sort of interesting idea behind this story is that should reviewers actually reproduce the experiments themselves before accepting a paper? On the one hand, there is workload involved. Where is the limit between what people could actually do? Like that reviewer who rerun the code, he ran something that you gave him out of the box. He didn't actually, I mean, he probably read the code to an extent, but do you see any future, any idea to be promoted that review processes should include some reproduction of results across different data sets, or sort of peer reviewing between labs or something like that?
I think it certainly helps. It can also hinder the process if the code is not written in a way that's clear and concise of what to do. With this, with the reproducibility package that we included, we had a how-to instructions on how to reproduce the figures and certain things to adjust. In our comments to the reviewers in the rebuttal session, we said if you change this line of the code, these are the figures that result, and you can see such and such. So it helped enrich the dialogue between us and the reviewers. I think when a paper is very heavily encased in mathematical derivations, it has the same issue of reproducibility. You have to sit there and go through the steps required in order to reach a particular result. And so that takes a time load and effort as well. So any result that I think can be reproduced probably should be reproduced for the review stage.
But then would it be better for the reviewers to reproduce the results, or for labs to, for example, publish articles in pairs, like, okay, lab X has come up with this great idea, done the code, lab Y has cross-checked with a different data set and came up with the same conclusions? Would something like that be the way forward?
Yeah, I would think that in the review, for peer reviewing, where it's unpaid and it's volunteer work, it's too much of a burden to say, okay, you reproduce this work. Instead, before it's submitted, I think a good idea is to have somebody in the lab that's not related to the work try to reproduce the work from the description in the paper to see if the paper meets or has details that are missing that should be included and so on. I don't think I would want, as a peer reviewer, to be told, okay, you need to reproduce this entirely.
No, exactly. But then there is like lots of research that goes through the reviewing process, which can be argued against afterwards. So, what's the way forward? I mean, yeah. Okay. Yeah.
More questions?
Actually, so Bob, I have a question. Do you have, for people here that want to do this at the first stage rather than in the revisiting stage, do you have some recommendations about how people should think about doing their research in order to make it reproducible in the first place?
Yeah, I find myself having a impetus to code first and then think later about what I've done. And it's often, at the time when it comes to submission, I have to spend a lot of time unraveling what I've done in order to make it reproducible. So if you think about, okay, this is going to be a reproducible paper, think about that first and start to structure the code accordingly, create functions, libraries, etc., include comments in the code so you don't have to spend so much time later on. And it also helps debugging while you're building the code up from the ground. But I mean, Van der Waal and his reproducible research in signal processing is a very helpful resource that was in the Signal Processing magazine for what makes something reproducible. And yeah, it's not easy. It depends on the research questions you have to ask too in the discipline.
Mm-hmm.
And whether, if you need to share a data set that's private, that hurts reproducibility as well. So do you include features with it or what type?
Okay.